Okay, so good morning everybody. Let's begin. So yesterday we looked at this very artificial problem of a particle trapped in a square potential well, and the motivation, what I billed as the reason for discussing these problems, was because these potential wells with sharp edges, was that it enabled you to solve some simple problems which illustrated features of quantum mechanics which are general, which would survive to other more realistic potentials. So, but the amount of physics you can do with a single square well is rather limited. There is some physics you can do with it, and I would urge you to play with this, to do things like supposing that your state your state is a linear combination of two adjacent stationary states, so that there is some motion. See that the particle moves to and fro across the well at about the speed, with about the period that you would expect. The energies in that square well are proportional to the square. They go like n squared of some integer, whereas the energies in the harmonic oscillator potential well go like n. That's to say, when we took this simple case of the infinitely deep potential well, the energy levels go like n squared, not like n. So that gives you very different behavior from the simple harmonic oscillator, and I think it's interesting to investigate that in the to try and recover classical results and see how that dependence of the energy levels on n squared rather than on n manifests itself in the bottom line. But we won't take time to do that. The lecture course is short. We're going to move on to this problem, which is more fun, and will allow us to understand how an ammonia maser works, which is a timekeeping device and was the first mazing lasing device. So what we do here is we imagine, so first of all we're going to solve an abstract problem, and then I'll explain why this is relevant for ammonia. We imagine we've got two potential wells which are divided by some barrier. Ideally, these potential wells would only be a finite depth, so the walls here would cruise off like this with V0, but the computations are made much easier if we let these walls go off to infinity. So the potential goes off to infinity. If you go to left of minus x is minus b, or right is of x is plus b. The potential is 0 here, the potential is V0, some number there. So this is basically two of these square wells put adjacent to each other with a finite, so there's only a finite barrier between the two. And nothing essential is changed, just the computations are made a bit easier by making these go off to infinity left and right. So what are we going to do? We want to find, again, the stationary states, the states of well-defined energy for this system, because they will have an interesting property, which will lead to the ammonia maser. So again, here is the origin, x is 0. This potential well is symmetrical on reflection around the origin, so it's an even function. The potential is an even function of x. That guarantees that the parity operator commutes with the potential energy operator, which guarantees that we can look for states of well-defined parity. So the stationary states could be eigenfunctions of P, so they have well-defined parity. By the usual argument that commuting operators mean we can find a complete set of mutual eigenstates. And we're going to assume, so there will be states which have even parity, there will be states that have odd parity, and as yesterday, the equation we have to solve is minus h bar squared over 2m d2u by dx squared plus v of x u is equal to eu. So we have to solve this equation, and we're looking for even functions and we're looking for odd solutions. We are going to assume that we're going to look for states which are low enough in energy that they are, as it were, bound by either this well or by this well. As I say, they're classically forbidden in this region. So we're going to look for states which have less energy, with E being less than this barrier height. So that classically the particle will be stuck in one well or stuck in the other well and couldn't go between the two. As we'll see, quantum mechanically it will go between the two. So that being so, the solutions, so what does that mean? That means that we've got d2u by dx squared, well, d2u by dx squared is going to be 2m over h bar squared v naught minus e times u, and this quantity is going to be positive when we're in the middle between when mod x is less than a. So this quantity here is going to be greater than 0, and that means that in this middle zone, the solutions to this equation are going to be things like e to the plus big kx. So this means for mod x less than a, we're going to have u goes like e to the plus or minus big kx. This is what we wrote down yesterday, where big K is the square root of 2m v0 minus e over h bar squared, okay? Or, because we're looking for solutions of well-defined parity, and these objects don't have well-defined parity, we can take linear combinations of those, and we can say, or, looking for well-defined parity, we can say u goes like cosh kx, or shine big kx. So these are the solutions of well-defined parity to that very boring differential equation, given that this quantity here is positive. So those are the solutions. We know that our solutions will have that form in that middle section as drawn up there. This is x equals a. This is x equals minus a. And then in the allowed regions, B will be somewhere over here, right? In the allowed regions, either side of the central barrier, we know that we will have sinusoidal behavior. There we'll be trying to solve the equation. So this is for mod x less than a. If mod x is bigger than a and less than b, we will be trying to solve d2u by the x squared plus nothing times plus v being nothing in that zone times u equals 2m over h bar squared e times u. So we're going to have solutions like sine kx plus some phase constant, where k is going to be the square root of 2me on h bar squared. And this is, so if I put in a phase, an unknown phase, this is an unknown phase here, then this sinusoid will represent any linear combination of sine and cosine, and so will be a general solution to this. Sorry, no, that's correct. I want E to be negative, right? Sorry, no. E is positive, E is positive, E is positive. Yes, there's a minus sign. There's a minus sign here coming from the minus h bar squared over 2m. So that's why there's a minus sign here. And that's why we have this sinusoidal behavior. Right. So we know what the solutions look like in the middle. We know what the solutions look like on the sides, and all we have to do now to fix everything up is make sure the boundary conditions are satisfied where they join. So we say that at x equals a, we have to make sure, as yesterday, that our wave function is continuous and has a continuous derivative. So the continuity of the wave function, let's specialize on the even parity case. Continuity of the wave function is going to say that cosh times Ka must equal b, that's my constant that multiplies the sine, times sine Ka plus phi. That's the continuity of u. And then I have to deal with continuity of the gradient of u, as yesterday. So we have that k shine Ka is equal to kb cos Ka plus phi. So we are not really very interested in B. It's the same sort of setup as yesterday. We're not very interested in the constant B. Yesterday we had a similar constant A. We're very interested in the value that K takes. And this thing here, big K, as yesterday, can be expressed as a function of little k. So the name of the game is to get rid of B. So we divide this equation by this equation. So 1 over 2 leads us to the conclusion that the hyperbolic coth of Ka is equal to K over K times the, sorry, I'm doing which division, sorry, I've got that the wrong way up. So that becomes big K over little k, right, because I am taking this equation and dividing it by this equation. So this K was on the bottom, as it were, and I brought it up to the top of the other side, times the tangent of Ka plus phi. And now we have ourselves, no, we haven't quite yet, because there's one thing we haven't fixed, which is we need to find out about this phi thing. What do we have to do with the phi? Phi has to be chosen so that the wave function in that right-hand zone vanishes at x equals b. Remember when we had the infinitely steep sides, we concluded that the wave function vanished adjacent to the rise to infinite potential energy. That was the thing, the point we finished on yesterday. So what we can say is that at x equals b, we require, because the potential is about to go infinite, that u equals 0. So that means that sine kb plus phi is 0, and kb plus phi is, so that, what does that imply? It implies that kb plus phi is some integer number of pi's. So that tells us what phi is. It tells us that phi, obviously, is r pi minus b. So we put this information into here, and we have our equation. Well, while we're doing it, it's probably a good idea to express big K in terms of little k. So we have expressions for big K and little k on the board. Let's work out exactly what we have, actually. So big K is the square root of 2m v0 minus e on h bar squared, which we write as 2m v0 a squared over a squared h bar squared minus 2me over h bar squared is in fact little k squared. And yesterday we identified this object as a dimensionless constant w. So this thing is the square root of w over a squared minus k squared. And so when I take this equation here and that result there in the right-hand side and this result here to get rid of those big k's, we discover that the hyperbolic cotangent of, I want big Ka, which is going to be the square root of w minus Ka squared, is equal to, on the right-hand side, big K over little k, which is going to be the square root of k, sorry, square root of, what am I talking about? Of big W over Ka squared minus 1 times the times the tangent of r pi minus k b minus a. And now we have what this is. So W is the dimensionless constant that characterizes the potential wells on each side. as yesterday. K is the thing of interest to us because it controls the energy. It determines the energy of the stationary state and is the only unknown in this equation. Everything else is known. So what we have here is a pretty ghastly equation whose roots determine the values of K, which in turn determine the energy. And as yesterday, the way to solve this is graphically to plot the left-hand side of the equation and the right-hand side of the equation as separate curves and see where they intersect. And I live in hope that my computer has this here. So, oh, the computer may have it here, but it didn't come up. Dear, the system has perhaps gone to sleep. Is anything showing? Yeah. Not, oh, but meanwhile my computer has gone and buried its... here we go. Right. So that should show, it's very faint from here, it's warming up, right? But that should show the two sides of the equation. The right-hand side of the equation... sorry. I'm now concerned that this is not... Right, that was that problem. Right, we need to go further down. It's not the right solution. Here we go. So here is the double potential well, and each of these curves is the right-hand side of the equation. It's coming down like this, and there's a different one because we have this tangent. So the right-hand side of the equation contains a tangent which goes to 0. We can forget about the r pi as a matter of fact, right? Because the tangent of r pi plus an angle is the same as the tangent of the angle. So I could write this, I probably should write this, as w over ka squared minus 1 times the tangent of this angle here, k b minus a. And there's a minus sign out front here, which is that minus sign. Okay, so you can add an r pi to a tangent and you don't affect its value. So this tangent keeps having zeros, right? As k increases, this tangent hits pi, 2 pi, 3 pi, etc. The argument of this tangent hits pi, 2 pi, 3 pi, etc. And the tangent vanishes. And those give you the points where these vertical lines crash down through the origin. These points, these points, these. That's why there are many branches. The other thing that's happening here, so the dotted line there, is, sorry, there are two, yeah. Focus for the moment only on the top curve because this thing's, so there are two curves. Where is this? I think this thing needs a new battery. There are two curves running horizontally, almost horizontally, a dotted one and a dashed one. The dotted one is the one we should look at, the one that curves upwards at the end. That is a plot of this coth. All right, so if W is fairly large and Ka is fairly small, then we're looking at the coth of a large number, and that's always 1. So this thing runs along at 1, and then eventually, when Ka becomes on the order of W, we're looking at the coth of something smaller than a large number, and that then goes up towards infinity. That then goes up towards yeah. So that's what's happening there, and the magic values of K are given by the intersection of the dotted line and the full lines coming down, and you can see you get a series of energies. There's only a finite number of them because when Ka becomes bigger than W, this square root goes imaginary, and we no longer have any solutions to the equation. Bad things happen here too. So there are only a finite number of energy levels if the well has any finite value of W. If we would repeat all this, so that's what we have. We have a finite number of energy levels. This is for the even parity case. If we were looking for the odd parity solutions, so for odd parity, what would happen is that the only thing that would happen is that this would become a shine, and that will become a cosh. Everything else would stay the same. So that the only thing that would happen as we followed through this logic would be that this koth would become a than, a hyperbolic tangent, all right? So this is even parity. You can follow through the algebra afterwards, but believe me, I think it's very plausible that all that happens is because you're swapping over a cosh and a shine, this becomes, for odd, we get than of this square root equals minus the square root, etc. So the vertically crashing down lines remain the relevant lines. The right-hand side hasn't changed, but the left-hand side has changed. So it starts off as the tangent, the hyperbolic tangent of a large number, i.e. 1, and then it becomes the tangent of a smaller number as Ka becomes comparable to W, so it turns downwards, not upwards, because, right. So the point now, the crucial physical point is, the crucial point that has physical consequence, is that when Ka is small, in other words, and K is a measure of the energy, right? The energy is proportional to K squared, because h bar K is the momentum of the particle as it rattles around inside this well. So the energy of the low energy solutions are associated with these things come in pairs. The energies come in pairs, agreed? Because we have the even and odd parity things intersect at low K almost exactly in the same place. On that diagram you can't see the distinction. As you get to higher values of K and the particle is only marginally bound, has an energy which is comparable to V0, the two curves for the right and the left sides diverge, and you can see you get different values of K. So what's the key thing is the solutions come in pairs. Because we had two potential wells, we get two adjacent solutions. In fact, if we had three potential wells, we would get three. If we have an infinite number, we would have an infinite number. And this is, in solid state physics, this is crucial because in a crystal you have 10 to the 24. You have some vast number of potential wells, one for each atom, and you get a vast number of solutions all crowded together. Anyway, we just have two wells. We have a pair of solutions. They come in pairs of similar energy, very similar energy, similar E. So one is even parity, and this actually will be the lower energy solution. It has the smaller value of K, you can check from the diagram up there, and one for the odd parity, and this is the higher energy. So the lowest energy, so for this system, for a particle trapped like that in a well, what do we have? We have a lowest state, and just above it, which is of even parity. So the ground state, well, here we are, we've got a picture here, I think. The ground state, so the top diagram there sort of shows these wave functions. We have a sinusoid on the right, a sinusoid on the left. The ground state is the two upper full curves. It's two sinusoids with a depression in the middle where the barrier is and the particle's classically forbidden. And then at an energy just a tiny bit higher, you have a very similar pair of sinusoids. They are in fact subtly different values of K, so they're very, very subtly different. But essentially, to a very good approximation, the odd parity state is the same as the even parity state, except reflected around the origin, so that it becomes negative on this side. So we have two states. We have so the wave functions are going to be what we'll call them u plus of x, which is the even parity case, and a u minus of x, u e of x and u odd of x, which is the odd parity case. If we take linear combinations of these two states, we get two other states, psi plus, which we'll say is 1 over root 2 of x, which is u even of x plus u odd of x, and psi minus of x. So if we take, so a psi plus is the sum of those two wave functions up there. So it vanishes on the left and has a non-zero value on the right. So this is state of being on the right. And this is the state of being on the left. Because if you take them away, they add up on the left and they subtract on the right. If we actually put the particle into the right-hand well, we will set our system up in this state psi plus. This state psi plus is not a stationary state. It is not an energy eigenstate because it's a linear combination of two eigenstates of different energy. So if we drop it on the right, what our initial condition at t equals 0, this is what our wave function looks like. What does our wave function look like generally? Psi of x and t is going to be 1 over root 2 times u even of x e to the minus I e even t over h bar, the usual boring time evolution of a stationary state, plus u odd of x e to the minus I e odd t over h bar, which we can write more conveniently as e to the minus I e even t over h bar over root 2 u even of x plus u odd of x e to the minus I e odd minus e even t on h bar. And the crucial thing is that if we wait long enough, if we wait such a time that the argument of this exponential becomes equal to pi, we'll be looking at e to the I pi, which is minus 1 here, and our state will have evolved into some phase factor, who cares, times u even minus u odd, which is the state of being on the left. So after a time, the time required for this to become pi, which is t equals pi h bar over e odd minus e even, the particle's on the left. And you can see that this will go on forever. You put the particle in on the right, it's not a stationary state. After this time, it moves to the left, and then after twice this time, it will have come back to the right. It's going to oscillate between these two wells forever and ever, according to this theory. And crucially, the time scale is long. It takes a long time to get from the right to the left if this energy difference is small. And we've seen that this energy difference is small. Right? So this energy difference being small means that this time scale is long. When is this energy difference small? It's small when the barrier between the two wells is high. So what we say is that the particle takes a certain time to tunnel through that barrier. So we say that the particle tunnels through the barrier. In a time which grows very rapidly as a fact with V0, with W, with the height of the barrier. So a high barrier or a wide barrier means it takes a long time to get through, but according to this analysis, it will eventually get through. Okay, so that's just a toy problem. Now let's see what the hell that's got to do with the real world. By talking about ammonia. Somewhere here we have a picture of ammonia. So ammonia is a... we don't have a picture of ammonia. No, sorry, I've somehow left it out. Okay, so what does ammonia consist of? It consists of 3 hydrogen atoms and a nitrogen, so these are H's, and it consists of a nitrogen atom. And the 3 hydrogens form some kind of a triangle, roughly speaking, and the nitrogen atom sits, well, this is the classical picture. We'll see quantum mechanical picture isn't like this, but this is the classical picture. We think of the nitrogen atom as sitting either above the triangle formed by the hydrogen atoms or below the triangle formed by the hydrogen atoms. Now this is a complicated system. It's got 4 nuclei and 10 electrons, and so it's a really complicated dynamical problem. But next term, in the next course, you will discuss a thing called see a thing called the adiabatic approximation, which is what chemists use in order to understand the dynamics of complicated systems like this. It allows you to treat all these bonds between the nuclei, which are provided by the electrons, as springs. So what we can do, what chemists routinely do, is they calculate the energy of this molecule in what's called a clamped nuclei approximation. So they say, let the nuclei be, let them be here, and let's calculate the energy. And you can do that for the nitrogen atom, for the nitrogen nucleus being at every point along a line that passes through the centroid of the triangle, right? So imagine doing that. That leads to a potential energy curve if you like, for the nitrogen nucleus, which is going to be something, it turns out, sorry, it's not obvious that it's going to be, but it turns out to be something like this. So there are 2 wells, the lowest potential energy when it's an appropriate distance either above the plane or below the plane. There are 2 wells, and there's sort of a barrier in the middle because it isn't comfortable being in the middle of the triangle formed by the hydrogens. So we have this kind of potential energy curve, and now we know what the energy levels of this molecule are going to look like, because we know that there are going to be even parities. The stationary states are going to divide this. It's obvious on geometrical grounds this is symmetrical, that this well looks just like this well, because there's no fundamental difference between above the triangle and below the triangle. So we know the solutions are going to come in pairs. There's going to be of even parity solutions and odd parity solutions, just like in our square well. So we also know that if we start with a nitrogen in this well, so we start with a nitrogen, say, above the triangle, it's going on some characteristic time to move over here, and then it's going to move back there, and it's going to oscillate between above the triangle and below the triangle. So if we start it in either above the triangle or below the triangle, it's going to oscillate between the 2. Those who've done chemistry will know also that this nitrogen is going to be carrying a negative charge, and these hydrogens some amount of positive charge. So what are we going to have? We're going to have an oscillating dipole. This molecule is going to have a dipole moment because of the electronegativity of the nitrogen. And it's going to be an oscillating if we start it in this state of being above the triangle, it's going to oscillate to and fro. And what does an oscillating dipole, electric dipole, do? It radiates. So this thing is going to radiate, and you will be able to, if you know what this potential surface looks like, you'll be able to calculate the frequency at which it's going to radiate, because the frequency at which it's going to radiate is going to be given basically by this formula here for the half period to go from there to there, right? So twice this time is going to be the period of a complete oscillation, and that's going to be the period of the radiation. Okay. So, so the molecule, if started, it's a dipole. So started on top, if you can achieve that, it's going to be an oscillating dipole. And the experiments lead to the conclusion that the frequency, nu, is about 150 megahertz. You can measure it. So it's a source of microwave radiation. From this 150 microhertz, you can also work out what the change in what this energy difference is. So E odd minus EE turns out to be about 10 to the minus 4 electron volts. So that's an energy difference which is small compared to the thermal energies of molecules just here in the room, right? At room temperature, the thermal energies of molecules, so K, the Boltzmann constant, times T, of the room temperature, is something like 0.03 electron volts. So this is much bigger than E naught minus EE. What does that mean? From your statistical mechanics course, you either know now or will soon know that means that we expect at room temperature there are essentially equal numbers of molecules in the even and the odd states, right? Because the thermal energy, the energy required to go from the ground state, this is the ground state, or this is the energy of the ground state, to the first excited state, is less than the characteristic thermal energy knocking around in the room. So there will be large numbers of molecules in both these even and odd states. And the idea behind an ammonia maser is that is to find a way of separating the molecules which are in the excited state, the odd state, leading them into some kind of a resonant cavity where they will then, because they're in the excited state, they will decay into the ground state. If you leave them, if they're left alone, they will decay into the ground state, emitting a photon with the balance of the energy, right? So they will radiate away at 150 megahertz. So that's the strategy behind a maser. So in a maser, to get a maser, you have to isolate roughly a half of the molecules in the first excited state. And the way you do this is you exploit the fact that, let's just imagine putting these molecules into an electric field. So we're going to put the molecules and the strength of this electric field I'm going to denote with curly E to distinguish it so that electric field is distinguished from energy, ordinary E, Roman E. Okay, so we put these molecules into an electric field E and ask ourselves, how does that change? Since these are dipolar molecules, right? These molecules are electric dipoles. We're expecting that changes the energy of the molecules, putting them in a field, and maybe we can get them separated by exploiting this fact. So you put them in an electric field and ask, so how does that change we're doing quantum mechanics, so change in energy means change in Hamiltonian. So we have to ask ourselves now, how does this change the Hamiltonian of these molecules? What term in the Hamiltonian is introduced by this electric field? And the way to do that is to think in terms of the Hamiltonian, write the Hamiltonian in the basis. So we're going to let plus be, so it's going to be mathematically 1 over root 2 of the even parity, the ground state, plus the odd parity, no, using a different notation, even parity plus odd parity. So this is the ground state, this is the first excited state. This linear combination is we're going to call it plus, and it'll be the state in which the molecule is definitely above the triangle. And similarly, minus is going to be 1 over root 2, even parity state minus odd parity state is going to be below. So this is below triangle, this is above. This is exactly what we did over here with our psi plus and psi minus. We were working there with wave functions. Here we're working with the underlying kets. The thing is, the dipole moment, if the dipole moment of these two states have opposite signs, because this one has the negative charge at positive z, and this one has the negative charge at negative z. So they have opposite dipole moments. And let P now be, P be the dipole operator. It was the parity operator earlier on, but now let it be the dipole operator. Then these states are going to be eigenstates of this dipole operator. They have well-defined dipoles. P plus is in fact going to be minus QS times plus, where what am I saying? I'm saying this is some charge, this is some distance. The product of a charge and a distance gives me units of dipole, electric dipole moment. I've got a minus sign here because this state I said had a negative charge above at positive z, so the dipole moment points in the opposite direction to the location of the nitrogen atom, and therefore this one has a negative dipole moment, and this eigenvalue, right, is the dipole moment. This is the eigenvalue of this operator because this thing is a state of well-defined dipole moment, and this is where the dipole moment appears. And basically, this is just some number which has the dimensions of a charge times a distance, which, the charge is going to be on the order, it's going to be some fraction of an electron charge, and this distance is going to be this characteristic size of the atom, 1/10 of a nanometer. Similarly, P minus is going to be plus QS minus. So this encapsulates the crucial point that these two states have oppositely signed dipole moments. What is the energy of a dipole in an E field? Well, the answer is that the energy is minus, this is just classical physics, is minus the field times the dipole moment. So now we know how much the energy of this state and this state are changed by the electric field. It's given by this here, where we put in those kind of eigenvalues. So now what we want to do is write down the matrix that represents the Hamiltonian in this plus-minus basis. So we want to write the Hamiltonian as plus H plus, a matrix. This is a complex number, right? Plus H minus H plus. So these four complex numbers we want to write down. That matrix. And the Hamiltonian consists of the Hamiltonian of the undisturbed nitrogen molecule plus the contribution here. This is plus the contribution here from the electric field. What do we have for the undisturbed? Let's calculate this separately. So I need to calculate what plus H plus is for the isolated atom. Well, that is going to be 1 over 2 even, whoops, because these are linear combinations of the eigenstates, even and odd, even plus odd h, even plus odd. Right? Because this is this, this is this, but h on this is an eigenfunction of this operator, if this is the isolated operator. So we get h on even produces e even times even. Even is orthogonal to odd, but meets up with this, so we get an even. And h on odd produces e odd times odd, which is orthogonal to this, but meets up with this to produce an e odd. So at the end of the day, we get a half of e even plus e odd, which is the average energy, let's call it E bar. Similarly, we have that, let's have a look now at plus h minus, the off-diagonal element. That is going to be 1 over 2 even plus odd h even minus odd. So things are rather similar, except we now get from here, here, and here, E even, and from here, here, and here, we get minus E odd. So we get a half of E even minus E odd. Which I think I have been calling, we're going to call this minus A. So A is, so we're going to call, this is the definition of A, and we're going to put this minus sign in here because we know that the odd energy is bigger than the even energy, so this quantity here is a negative number, and putting that minus sign I get this positive number. So this matrix up here, what's it looking like? It's looking like E bar from here, A. This is a Hermitian matrix, so what appears down here has to be the complex conjugate of that real number A, in other words A, and we will find that this one is also E bar. That's for the isolated atom. Then we have to add on to it the contribution from this, but this thing is an eigenfunction of P, so there are only contributions down the diagonal. There are no off-diagonal contributions from this additional piece to the operator, to the Hamiltonian. And what I have is plus, what I need is the dipole operator, so I have P on plus, which produces minus QS times plus. So this minus sign and the minus sign that I've just spoken cancel, and we get plus Q curly, and here we get minus Q curly ES. So this is what the Hamiltonian looks like in this basis. I'm running out of time, so let me just sketch how the thing goes. So what we have got is an explicit expression for the Hamiltonian in the presence of an electric field. What we would like to know is what the energy levels are, right, that result from this, and how those energy levels vary as a function of the electric field. But that's a dead cinch. What you've got up there is a 2x2 matrix. Anybody can find the eigenvalues of that 2x2 matrix, and those will be the energies that the molecule has when you stuff it in this electric field. So we find the eigenvalues of this matrix, and we plot how they depend on curly E. So what they actually are is the average energy plus or minus the square root, I believe, of A squared minus Q. Just make sure I didn't make a mistake there. Yeah. So these are the possible energies. And if we plot this graphically, what do we see? what we see here, we have the strength of the electric field. We find that we have solutions that behave like this. Here we have E bar plus A. Here we have E bar minus A. And here we have the strength of the electric field. This is just a graph of those two things. You can easily check that that's the case. Here, of course, is E bar. So this is the ground state. If you switch off the electric field, we have two states, here and here, separated by this small amount, which is 2A. As you switch on the electric field, the energy of the ground state goes down, but the energy of the first excited state goes up. There's a lot of interest in the way in which this energy behaves. Here it's behaving quadratically as a function. This is a sort of parabola as a function of E, and eventually it becomes a straight line as a function of E on both top and bottom. And what that's telling you is that in this regime here, the even state, the ground state, which is the even state, has no dipole moment intrinsically because the particle is equally likely to be above, the nitrogen is equally likely to be above or below the plane. So in the ground state, there's no dipole moment. You switch on the electric field and you make a bias so that the upper field, say, the upper position gets to have a lower energy than the lower position because the electric field is pushing it that way. So the nitrogen starts to spend a bit more time above than below, and now the molecule acquires a dipole moment, right? Because the nitrogen is not spending equal time above and below. So it acquires a dipole moment. The magnitude of this dipole moment is proportional to the energy, and therefore the energy that you get, the change in the energy, which is equal, as it says up there, E is minus electric field times the dipole moment, becomes proportional to the dipole moment squared. So that's why we have a quadratic dependence like this. Once you're in this regime, you have a fairly strong electric field. You've made such a strong bias, you've made being up so energetically more favorable than being down, that the nitrogen spending all its time up. The dipole moment is now independent of the strength of the electric field because the increase in the electric field doesn't cause it to spend any more time up or it's already spending all its time up, so that the energy becomes proportional to this. How do you make your maser work? You make your maser work, well, the fact that the energy of one of these goes down and the energy of the other one goes up means that as the field increases, that if you have an inhomogeneous field, if you pass your beam of NH3 molecules through a region in which the electric field is varying in strength. If I put so I have some sort of capacitor plates. I have a pointy thing, right? A needle and a cup. Then the electric field the field lines go like this, and we have a high field up here and a low field down there. So I have a region of inhomogeneous field. The ones in this state are going to be bent, they're going to be bent upwards. They like the field, it lowers their energy, so they move into the region of high field. These ones move into the region of low field. So this is the ground, and this is the excited. And then you can put these ones into your resonant cavity and hear it sing. So there's an example of how with a very simple-minded model, you can explore some quite interesting physics, and some physics which is very, very inherently quantum mechanical. This energy levels coming in a couple of in pairs. Because we have even and odd parity states. This ability of a molecule which you would think was inherently dipolar to in the ground state have no dipole moment because the nitrogen can be simultaneously above and below. All of these features are very quantum mechanical, and with a simple-minded model we're able to explore them. Okay.